These notes will teach you what you need to know about systems of objects and Newton's laws as they apply to systems of objects, but we'll specifically look only at Newton's second law as it applies to systems. The first thing to get over is that the word systems can sound scary or confusing. It's just a fancy word for a group. So a system of objects just means a group of objects, and usually guess how many objects are in our group. Most commonly, that just means two objects. So when you see system of objects, you don't freak out, you just think, okay, two objects. Could be 3 or 4, could be a large number like a bunch of particles in space, but in our class, it's usually two objects. That's what this fancy word system means. Here's an example. This example has 3 objects. Each one has a mass. They could be different. So you have M1, M2, and M3. This object is moving in one direction. This shows that they can have different velocities. The different objects each can have its own individual velocity. An object could be stationary, like M3 is stationary, and they can collide with each other. So M2 is going to crash into M3. They can interact with each other. So they can have different masses, different velocities, including sitting still, and they can interact with each other. Now, in books and in notes, you need a way to show what's in the group and what's not in the group. It's kind of like being in an exclusive club. The group will have members. And there are 2 common ways to do this. Very often a teacher or a textbook will say, well, draw a circle around the group. And they'll do something like this. And that indicates the members that are in the group and what's not in the group. So in this case, the table is not in the group. And there's nothing wrong with that, but it can become kind of tricky if objects are touching something else, to squeeze that circle in there. But that defines what's in and what's not in the group. When I remember to do it, I think it's better to use color, because then this works even if the objects in the group are touching something outside. So here, there are 2 objects. Everything about them is in red, so the group or system is anything that's in red, and since the table's in black ink, it's not in the system. Once you have a group, then you have a center of mass. We've learned this at the very beginning of this chapter. Here's an example. 3 kilogram mass, 1 kilogram mass. The center of mass, of course, is going to be closer to the 3 kilogram mass. And just to remind you, that's like a balance point. So if these were on a massless stick, this is where you put your finger so that it would balance. The center of mass can move, and that was not taught earlier, so this is a new idea. That center of mass can move if these objects are moving. For example, if we have a 3 kilogram as a car, and it's moving to the left, and the 1 kilogram is moving to the right at the same speed, well, the center of mass will move. And you can quickly figure out up here that, let's say this distance is 1 inch, then this distance has to be 3 inches, right? Since this mass is 3 times bigger, the center of mass will be 3 times closer. So this, in other words, from the center of this one to the center of mass is 1/4 of the total distance. So you get that 3-to-1 ratio in these distances. Okay, so now imagine these 2 masses moving apart from each other at equal speeds. In order for this center of mass to still be 1/4 of the distance from here to here, it has to move. It has to move this way. If I move these very, very far apart, center of mass will move over to here, over left, so that it's always 25% or 1/4 of the distance between them. In fact, it's possible, it's not hard to figure out that the velocity of this center of mass has to point left, right? You should be able to figure that out. You pause the video and think about it. You could even try to calculate it if you think you can figure out, guess how to calculate the velocity of the center of mass. But you should, even without calculation, quickly see that the center of mass has to move left, because there's more mass moving left than there is moving right. So the center of mass is moving left. But what speed would it have? Well, it's possible, it's not too hard to show that the speed of the center of mass here would be 5 meters per second, and the direction would be left. So what we've done here is we've kind of reduced a system of objects to single descriptors, or things we can use to describe the whole system using single quantities. So first, the total mass of this system would be what? It would be 4. And the center of mass is here and moving left at a speed of 5. So this is like a single 4 kilogram car going left at 5 meters per second. Okay? And we'll come back to this diagram in a minute and use it for our connection with Newton's second law. All right, these next notes will distinguish between internal forces and external forces. Internal forces are what one member applies to another. For example, two objects could collide, like two billiard balls on a pool table. You could have, say, two stars or a planet and a moon. They could apply gravity force to each other. This would be an internal force because this gravity force is being applied to the right-hand object by the left-hand object only, and both of these are in a system. Okay? If these two balls are in a system and connected by a spring, that spring would be part of the system, and the spring force would be considered internal. So everything in here is in the system. The spring force between them, whether you stretch them and it's pulling them together, or here the spring has been compressed and it's pushing them apart, that's an internal force. We distinguish those from external forces. It's pretty clear, obvious what that is. It's applied by something outside the system, like the table in that earlier diagram. If this object hits the table, then the table will apply an external force because the table is in black ink and we've defined it as being outside the system. You might ask, how do I know what's in a system or outside a system? Is that something from nature? And absolutely not. We choose in every problem what we want the system to be. And as you do problems, you'll understand how to pick that. It becomes pretty obvious. So this is an arbitrary decision made by people as to what is in a group or system and what is external to a system. All right, so here's an example of external forces. I've shown the system that we've chosen, as I said, in red. So here it's a larger car hitting a smaller car. This larger car is moving in the before picture, and they're on a road. The road is in black ink, so it's not part of the system. The big car crashes into the smaller car, and they stick together. So this makes a combined large mass moving to the right with one speed. The road, however, will exert a friction force on it because these tires are sliding on the road, and that friction force will point left. So that's an external force because it's applied by something that I have not defined as part of the system. Okay, and that brings us to our conclusion. That's center of mass. So I'll take you back to this earlier diagram. Here's our system, two objects. One is 3 times bigger than the other, so the center of mass is 3 times closer to that one. It has a center of mass. If the two objects start moving, that center of mass can move. And now look at what we've reduced this, more or less, complex system to. We can describe its mass with a single number, 4 kilograms. That's the total mass. We can describe its position with a single number, x center of mass, which might be something like 100 meters on a number line, for example. So it has a single position. We can simplify the system, which actually has two positions, right, to a single position, the position of its center of mass. This is very useful. That's why we do it. And that center of mass could move, so we can describe the velocity of the system as the velocity of the center of mass. We don't say 10 left and 10 right cancel out and make a velocity of 0. We want sort of the net motion of the mass, and since there's more mass going left than right, we say that the velocity is to the left, and it's weighted. This counts 3 times more than that, because this has 3 times the mass. So that velocity is weighted to the left. So we describe the system with these single numbers: mass by its total mass, position by the position of the center of mass, and velocity by the velocity of the center of mass. Notice these things are weighted by the masses. Okay? Velocity of the center of mass. And since there's a velocity, there could be an acceleration. If these cars are moving, their speeds are changing, then the center of mass could have a velocity and have an acceleration. So this whole system has been reduced to our familiar variables: single mass, single position, single velocity, and a possible single acceleration. So what Newton figured out was, if you have a system or group, you don't have to come up with a bunch of new laws. You don't have to apply his laws individually to each member. The center of mass itself follows Newton's laws, and that's how we greatly simplify the behavior of a system. And this is one of the ways you approach the rocket problem, where a rocket is shooting out gas to the left, but the main mass of the rocket is moving to the right. The center of mass of this, since these forces are internal, the center of mass has to stay stationary. All right, so the center of mass follows Newton's laws. So look at, this is our familiar second law, F equals ma. Or the total external force equals mass times acceleration. Well, here the total external force means external to the system. That part's easy and pretty obvious. What would the mass be? For example, if you're going to use F equals ma for an entire system, what would you use as the mass for this system? Well, of course, you'd use 4. So this means total mass of system. That's what goes in the m place, not the mass of one object in the system, but the total of the whole system. And for the acceleration, what's that going to be? The acceleration of what? This one? This one? And of course not. We need to describe this system by a single point that could have velocity and acceleration. In other words, it could have position, velocity, and acceleration, and that point is the center of mass. So when we say acceleration, we mean the acceleration of the center of mass. And we write that in symbols this way. Here's the F. Okay. Same thing we've always written, really. Total external force. That's what this has always mean in F. When we say F equals ma, that's oversimplified, and we understand we always really mean sum of the external forces. And here, instead of writing a simple m, we don't want to write just m because that makes it look like the mass of one particle. We write this, total mass. And then for acceleration of the center of mass, put our familiar symbol for acceleration, then we put a COM. And this is something you're expected to know for the advanced placement test, that Newton's law, all of Newton's laws, but especially the second law, that's the one that's most useful and most often applied, that the second law can be used for systems of particles as long as you understand the mass means total mass of the system, and the acceleration means the acceleration only of the center of mass of that system.